Welcome to this lecture on microfluidics and its fascinating applications in culinary and food science. Today we'll explore how microscale fluid manipulation is revolutionizing how we create, analyze, and understand food at the molecular level. Let's begin by understanding what microfluidics actually is. Microfluidics is the science and technology of manipulating fluids at the microscale, typically in channels with dimensions from 1 to several hundred micrometers. To put this in perspective, these channels are smaller than the width of a human hair, which is about 70 micrometers. Here you can see the scale comparison. The microfluidic channel is significantly smaller than a human hair. Why work at such small scales? There are several key advantages. First, we gain precise control over fluid flow and mixing at the molecular level. Second, we use tiny amounts of materials, reducing both cost and waste. Third, the high surface area to volume ratio enhances heat and mass transfer. Fourth, at these scales, flow is laminar rather than turbulent, giving us predictable fluid behavior. Let me ask you a question. How do we determine whether flow will be laminar or turbulent in these microchannels? The answer lies in the Reynolds number. Reynolds number equals density times velocity times characteristic length divided by dynamic viscosity. When Reynolds number is less than 2,300, we have laminar flow, which is smooth and predictable. When Reynolds number exceeds 4,000, flow becomes turbulent with chaotic mixing. In microfluidic devices, Reynolds numbers typically range from 0.01 to 10, ensuring laminar flow. Now let's explore our first major application in food science, emulsion formation. An emulsion is a mixture of two immiscible liquids, like oil and water, where one is dispersed as droplets in the other. Common food emulsions include mayonnaise, milk, and salad dressings. Traditional emulsification produces droplets of varying sizes, as shown on the left. Microfluidic methods, shown on the right, create highly uniform droplets with precise size control. There are several mechanisms for generating droplets in microfluidic devices. The T-junction is one of the simplest geometries, where two fluids meet at a perpendicular intersection. Flow focusing uses a constriction, where the continuous phase squeezes the dispersed phase from multiple directions. Co-flow involves parallel streams, where one fluid is injected inside another. This diagram shows a T-junction device. The oil phase enters from the top, and the water phase flows horizontally. At the junction, uniform oil droplets are pinched off and flow downstream. Here's an important question. What parameters control the size of droplets generated in these devices? The answer is that the flow rate ratio between the continuous and dispersed phases is the primary control parameter. Droplet diameter is proportional to the ratio of dispersed phase flow rate to continuous phase flow rate. Additionally, channel geometry and interfacial tension between the fluids play important roles. The capillary number, which compares viscous forces to interfacial tension forces, governs the droplet formation process. Capillary number equals viscosity times velocity divided by interfacial tension. Our second major application is spherification and encapsulation, a technique made famous by molecular gastronomy. Spherification involves creating gel spheres with liquid centers, often using sodium alginate and calcium chloride. Traditional spherification produces spheres of varying sizes. Microfluidic encapsulation allows precise control over both sphere size and shell thickness. What are the advantages of using microfluidics for this process? First, we get monodispersed capsules, where every sphere is exactly the same size. Second, we can precisely control the shell thickness. Third, we can create complex multilayer structures with different materials. Fourth, we achieve high encapsulation efficiency with minimal waste of valuable ingredients. Let me explain the chemistry behind gelation in these systems. Sodium alginate, which is negatively charged, reacts with calcium ions to form a cross-linked gel network. In microfluidic devices, this cross-linking occurs at the interface between the alginate droplet and the calcium solution. The gelation time can be controlled from milliseconds to seconds by adjusting calcium concentration and pH. Our third application involves using microfluidics for flavor analysis and extraction. Food flavors are incredibly complex mixtures of hundreds of volatile and non-volatile compounds. Microfluidic devices offer several advantages for flavor analysis. They enable rapid screening of individual flavor compounds in tiny sample volumes. They allow on-chip extraction and concentration of target molecules. They can be integrated with various detection methods like mass spectrometry or fluorescence. This schematic shows a microfluidic flavor analysis chip. The sample enters and flows through an extraction zone where target compounds are separated, then moves to a detection zone for analysis. One powerful technique is liquid-liquid extraction in microchannels. Two immiscible phases, typically aqueous and organic, flow side by side in a microchannel. Target flavor molecules partition between the phases based on their solubility. The partition coefficient Kd equals the concentration in the organic phase, divided by the concentration in the aqueous phase. Extraction efficiency increases with contact time and interfacial area, both of which are optimized in microfluidic devices. Our fourth application focuses on texture analysis and rheological measurements of food materials. You might ask, why is studying the flow behavior of foods important? The answer is that texture is one of the primary factors driving consumer acceptance of food products. Additionally, rheological properties affect how foods can be processed, packaged, and their shelf stability. Microfluidic devices offer unique advantages for rheological measurements. They require only microliters of sample instead of the milliliters needed for conventional rheometers. They can access very high shear rates that are difficult to achieve in conventional instruments. They enable in situ measurements during food processing operations. Shear rate gamma dot equals the derivative of velocity with respect to position. For Newtonian fluids, shear stress tau equals viscosity mu times shear rate. In a microfluidic rheometer, we measure the pressure drop along the channel and the flow rate. From these measurements, we can calculate viscosity and other rheological properties. Many foods exhibit non-Newtonian behavior, meaning their viscosity changes with shear rate. Shear-thinning foods like ketchup and yogurt become less viscous when sheared. Shear-thickening materials like cornstarch suspensions become more viscous when sheared. The power law model describes non-Newtonian behavior. Viscosity ETA equals consistency index, K times shear rate to the power of n minus 1. When n is less than 1, we have shear thinning behavior. When n is greater than 1, we have shear thickening behavior. Our fifth application involves creating advanced nutrient delivery systems using microfluidic fabrication. Many nutrients like omega-3 fatty acids, vitamins, and probiotics are sensitive to heat, light, and oxygen. Microencapsulation protects these sensitive ingredients and controls their release. Microfluidic devices can create multi-layer capsules where each layer has a specific function. The outer layer might protect against stomach acid, while inner layers provide controlled release in the intestine. Core shell structures offer several advantages for nutrient delivery. The shell protects the core nutrient from environmental degradation. Release kinetics can be controlled by varying shell composition and thickness. Delivery can be targeted to specific sites in the digestive system. There are several mechanisms for triggering nutrient release. pH-triggered release responds to the pH difference between stomach and intestine. Enzyme-triggered release uses shells that are broken down by specific digestive enzymes. Time-delayed release relies on slow diffusion of the nutrient through the shell material. The release rate, dMdt, equals the mass transfer coefficient K times area A times the concentration difference between the shell surface and the bulk solution. Our sixth application addresses food safety through rapid pathogen detection using microfluidic biosensors. Traditional microbiological methods for detecting pathogens can take several days. Microfluidic devices can detect pathogens in hours or even minutes. A microfluidic biosensor typically has a capture zone where specific antibodies bind the target pathogen, followed by a detection zone where the binding event is transduced into a measurable signal. Several detection methods can be integrated into microfluidic devices. Immunological detection uses specific antibody-antigen binding. Nucleic acid-based methods use PCR amplification of pathogen DNA. Electrochemical sensors measure changes in electrical signals upon pathogen binding. Optical methods detect fluorescence or absorbance changes. How sensitive are these microfluidic biosensors? The limit of detection LOD equals 3.3 times the standard deviation of the blank divided by the slope of the calibration curve. Modern microfluidic biosensors can detect as few as 10 to 100 bacterial cells per milliliter. This sensitivity is sufficient for most food safety applications where pathogen loads need to be kept extremely low. Let's discuss the materials and fabrication methods used to create microfluidic devices for food applications. Several materials are commonly used. PDMS, or polydimethylsiloxane, is flexible, transparent, and biocompatible. Glass is chemically inert with excellent optical properties. PMMA, or polymethyl methacrylate, offers low costs and good chemical resistance. Silicon allows precise fabrication but is more expensive. Different fabrication methods are used depending on the material and application. Soft lithography is the standard method for creating PDMS devices. Hot embossing is used for thermoplastic materials like PMMA. Laser ablation allows direct writing of channels into various materials. 3D printing is an emerging method enabling rapid prototyping of microfluidic devices. As we conclude, let's look at future perspectives and remaining challenges in this field. One major challenge is scaling these technologies from laboratory demonstration to industrial production. Cost reduction is essential for commercial viability, especially in food applications where profit margins are tight. These devices must be integrated with existing food processing infrastructure. All materials must receive regulatory approval for food contact applications. Despite these challenges, several exciting trends are emerging. Lab-on-a-chip devices can perform complete food analysis from sample preparation to detection in a single device. Smart packaging incorporating microfluidic sensors can monitor food freshness in real time. Personalized nutrition could use microfluidics to create custom nutrient formulations for individuals. Microfluidics is playing a role in cellular agriculture and the production of cultured meat products. Let me summarize the key points from this lecture. Microfluidics provides unprecedented control over fluids and particles at the microscale. Applications span the entire food chain, from production and processing to quality analysis and safety. Creating uniform emulsions and capsules improves product quality and consistency. Analytical applications provide rapid and sensitive detection of flavors, nutrients, and pathogens. Microfluidic rheometry enables texture analysis with minimal sample volume. The field must address scale-up and cost challenges to realize widespread industrial adoption. As we close, I'll leave you with a final question. What aspect of microfluidics in food science excites you the most? Is it the precision of droplet generation? The potential for rapid food safety testing? Or perhaps the possibilities for creating entirely new food experiences? The intersection of microfluidics and food science represents a frontier where engineering meets culinary art and nutritional science. Thank you for your attention, and I hope this lecture has inspired you to think about food at the microscale.